Let's see. So I'm here to talk about building a fast distributed log with a smidge of fault tolerance. And I'm going to talk about like the parts of this project that I personally find kind of neat, but also like the kind of unfashionable trade-offs we made along the way to kind of get exactly what we needed for us. To set some of the scenes, when I say fast, I think what I'm talking about is like in the like sub-millisecond, like microsecond level scale of things for completing transactions. And when I say smidge, I mean that sometimes there are situations where it will not recover until a human intervenes. So, great. And I did not start the timer. Hi, I'm Doug. I work at Jane Street, and I work on this distributed log called Aria. I've been working on it for the past 6 or so years. I have talked about Arya before, and we have at Jane Street. There's a Signals and Threads podcast. This is a podcast that we run, and there's an episode about state machine replication, which is very tied to Arya and kind of the way that we use it. There's another blog post about about how we test Arya, which is a much more like in-depth look at some of the things that we do. But today we're going to talk about like kind of the architecture and the weird architecture, I guess you could say. So I'm gonna start with a confession. I'm not an expert in distributed systems by any stretch. I've never taken a course on distributed systems. I have learned the fraction of what I know like about the field that I know today from just like being at the job at Jane Street. And about like earlier this year, I agreed to give this talk, and so like a week later, of course, I went and I bought a book, and I bought this book because I was like, oh, this book is, I heard it's a good book. It's gonna make me smart, and I can say I can be a smart, educated person. But like, instead, I think I'm not gonna do that. I'm just gonna like tell you what my experience is, because it's like these are my lived experiences. These are like what happens in practice and like the dirty, gritty stuff behind the scenes. And so if something sounds weird, it's probably me, it's not you. So let's start a little simple, which is like, what is a log? We were talking about distributed logs, but what is a log? It's an append-only data file. That's it, that's the whole thing. It is a file, it has data, you append to the end of it, and that's the only operation you can do. You can read from it, but you can't do any other mutation. Pretty common example is like a database will have a write-ahead log where they will write operations that they're going to perform so that they can persist in the disk as a way of recovering if there's a crash or something. Okay, what is a distributed log then? It's kind of like the multiplayer version of a normal log. So you can think of like many actors that are distributed somewhere, and they're all looking at the same log. So they all see these, they all have the ability to append, and more importantly, they all see all of the records in this log in the exact same order as each other. So there's a consistent view among everyone that sees this log. This is a property that is called total ordering. There is a single canonical ordering for this log, and it's probably, I would say, like the most important part of this talk is total ordering. When it comes to distributed logs, Kafka is a very popular distributed log that's available. A lot of the world uses it. A very common use case when you're dealing with logs is to have like a producer that is just kind of like dumping data onto a log, appending, and then maybe one or more consumers that are reading the log as more data is added. We're going to talk about some cases that are a little bit different than that. So let me start with, Jane Street is a bit obsessed with logs and historically allergic to databases. And Arya is not the first log abstraction that we have built. It's not the second, and it's also not the third. So there's a long history of people building their applications around some kind of log or distributed log mechanism. When it comes to the databases, we do use databases, but like for a number of reasons, they aren't as convenient. People don't really reach for them for small things. People will reach for like, logs or writing your data to an S expression and saving it on disk or something like that. This is starting to change, I think. People are, databases are really good and like easy to use, but there's a lot of power even still in building on top of a distributed log. And so I kind of want to hope to convince you of that a little bit here. So what I want to do is I want to give you my mental model for building on a distributed log. This is our log. It's got a bunch of stuff already appended to it. They're just, different records here. You can kind of imagine it as it contains different records from different components within a service. And so what we start with is we start with a state machine that we have built. And we're not interested in everything. We only want some of it. So we filter down to the things that we actually want. And we start at the beginning. We read this entry, we update our state, move on. Now, at some point, maybe the application that is running this state machine decides it wants to append to the log because it has received some sort of a outside effect or something, and so it's going to do that. It's going to kind of send that out. That's the little star thing here. But at the same time, this like other K is kind of coming in from a different spot, and that's a different producer producing to the same log. Everyone's kind of working in one log together here. The important thing is that we want to propose a change. We want to do something. We want to update state. But we're not going to update our state machine. We're just going to write down our intent to and then append it. So what happens here? These two kind of land in some order. We don't know what it is. Well, we know now. It's K and then star. And we're also not waiting for any sort of like acknowledgement that the write succeeded. So we're just going to keep going. And we read the next one. And we read the next one. And this is kind of where we have to start grappling with the fact that there might have been a race condition and K and star might have conflicted in some interesting way, but we handle that and we move on, and now we see our own message. And at this point, we can apply that update that we wanted to our own state, not back when we made the request. So that's like a kind of important aspect of this like flow of you're waiting for it to be on the log and then you apply it. So you also occasionally will want to like take a snapshot of yourself, because starting over from the beginning of time is like next to impossible. But from here on out, you can keep going, and the snapshot will let you start from there if you crash at some point and want to start over. So this is like kind of how I think about it. I think there are so many other ways that you can use distributed logs, but like this to me is like the pattern that is really exciting and fun to program and good at building complicated systems, and also kind of good at building easy systems too. So we like this pattern, but it has limitations. Cool thing, these logs are very flexible. You can put whatever you want in those records. You decide what the data is, and you also decide how it gets interpreted. And that there's a lot of like power and flexibility to that. The total ordering, again, total ordering, it gives you consensus. Consensus is such a hard thing it's such a hard problem because it's also so important. And if you already have a total ordering, the ordering is your consensus. Two things that might arrive at the same time in a race condition, one of them comes first, and it's on the log, everyone sees it in the same order, and everyone can at least agree on what who won the race. It's not that you don't ever have to deal with race conditions, but it does kind of like reduce the amount of thinking you have to do. Kind of like how type systems don't prevent all bugs, but they kind of do reduce a large class of bugs. Okay, but here's the problem. It's inherently a bottleneck. It's a bottleneck because when you want a total ordering, that ordering has to be decided by one thing. Like one computer, one processor somewhere in the world has to be the thing deciding that. And I am at least pretty sure that that's true. Again, no academic background. But that's a problem. That's like a bottleneck, right? And so how do you get around that? The common answer is like, well, you can shard your data. You can split it up into multiple logs. And you can, and that's kind of how Kafka works. You get lots of topics and lots of partitions, and you can throw tons and tons of data at Kafka. But each of those shards are their own total ordering. You don't get total ordering between the two. And if you want to try to construct a total ordering, it can be like very slow. It can be like, you can't do it like live as well as you might want to. So, okay. So that's where we made Arya. We wanted to make it as a platform that other teams at JStreet could build software on. The question is like, how far can we push a log that is fast, low latency, and has total ordering? So speed. We have a 30 microsecond round trip, like when it comes to a client that wants to append, and when they see that append come back, the medians are about 30 microseconds. There's an asterisk here because at this scale, if you're in like the next building in the data center, your network cost could push that up a lot. If you're in a completely different neighboring data center, it goes up even higher. So scale. We have gotten a single log up to 10 gigabits per second of throughput, totally ordered, which is kind of just the limit of the network card. This is just number of writes, number of appends to this log. And this is per Arya instance. And what I mean by per Arya instance is there is not just one Arya. Our goal was not to make a single log that would be suitable for every need forever. We've got like an Arya in different regions, in Asia, in Europe, in Americas. We've got some in the cloud. We've got some for special users who just need more. So, there is some amount of sharding, but like ideally, you can still get a lot out of that scale. Also, I just like super want to acknowledge that like this is not big data scale. Like when you're putting analytic data or like any sort of event data in Kafka, this is nothing, right? But there's still like a lot of there's still like a lot of use case that you can get out of just this, is what I'm trying to say. And reliability. I don't have a number here, but we have historically good uptime. You can take my word for it. And but reliability to me is also like predictable performance. Like we have 30 microsecond round trips, but if our tails were 10 seconds, then that sucks. Like you don't want to have to maybe wait 10 seconds a few times a day. So like having very predictable performance and having a reliable data retention story, these are things that people want to build on top of, or else they have to kind of find their own solutions on top of that. Yes, quick reality check. This is not like the backbone of JStreet or something. I think I've talked about this before and people sometimes get that impression. JStreet has like many systems, and they're all kind of built ad hoc, and they have different requirements and different teams that are working with other teams, and so there's a lot going on here. So this is not just this is just one piece in a large soup of RPCs and other applications. Okay, so let's peek into Arya. Wait, was I supposed to say something? No. Designing for speed. So let's talk about speed first. I talked about how you need a single point to determine the order. And so that's what this thing that's called the sequencer is. And so let's focus on the sequencer because there's only one of them. And the thing that we did, the thing that we found successful, is to make the sequencer as simple as possible. Like, push all of the complication as much as you can to the edges. So let's trace a path from this top client here. And you can see, hopefully, that it's starting to send data, and it's going to reach one of these injectors. And injectors are something that can do authorization, they can do rate limiting, they can take a large message and chunk it up into smaller messages. And then they fire it along to the sequencer. And so here's where the sequencer just does the very naive thing. It takes one message in its queue, and it puts a number on it, and then it sends that message out. And that number that it stamps is a strictly increasing number. And by doing that, you have established a total ordering of all of the packets. And that's mostly it. There's a little bit more that it does, but it would take a lot to get into all of that. The sequencer itself can far exceed a 10 gigabit network. It is nowhere near the bottleneck. But the number that it stamps is also the timestamp of its wall clock, which is kind of just a useful property from the perspective of knowing when something actually got to the sequencer. This little disk here, is the persistence. It is not a write to disk. It eventually ends up on disk, but there's a combination of a ring buffer in memory and a disk write below it. We do not f-sync on every single call. We'll talk a little bit more about why later. But eventually these publishers will get access to the data, and they will fan them out to the clients. And it's nice that we have these publishers, because we can scale them up to meet the read needs, since you usually have more reads than writes. Great. So if we look at this was the path that one message took. This is the 30 microsecond round trip that I had talked about. It does jump through a lot of things. And the one thing that's kind of interesting, though, is the client itself has two connections. It connects to an injector, and it connects to a publisher. But why two? Why not one? So we will get into that when we start designing for durability. And so what I did in this slide is I took that one node, that was a single node of Arya, and I copied it and pasted it 3 times. And so now we have 3 nodes of Arya. They all have sequencers, they all have injectors, they all have disks, they all have publishers. But you can note a few things. These sequencers are grayed out in the B and C, the second and third row here, those nodes, because they're not active. You can only have one sequencer, and that's the sequencer A. But maybe even a little bit more interestingly, the publishers in that first node are also grayed out. In our previous slide, they were doing something, and here they're not. And so we can kind of trace the path of this client one more time, this same client, and it's still going around to the injectors, to the sequencer, to the disk, the storage mechanism. But then there's this kind of network topology where we're replicating data to the other nodes. Then it reaches another node, disk, publishers, back to the client. And this is intentional, and this is why we have 2 connections. Because what it means is when you send data to the sequencer, you always receive it from another node in the system. And at that point in time, we know that that data lives somewhere on 2 different nodes. And as long as those nodes are not co-located, we have that much level of failure tolerance. We can lose one of the nodes and not worry about data loss. This is also kind of where the fsync thing comes in, because we're not really thinking about disk as much as the data being live somewhere else. And I talked about the 30 microsecond round trip. This is actually the 30 microsecond round trip. And the reason why it's so fast, another reason why it's so fast is we are using our own hardware in a data center we control, and special network cards that are low latency and user space networking to avoid talking to the kernel, and UDP multicast, which is a really great protocol for just sending one packet out and getting it to a bunch of nodes at the same time. These are things that don't work at all in the cloud, or I mean to some degree, but you can do this in the cloud. It's just not as performant. So we're really leveraging things that we know, because these are all common patterns in trading and market data dissemination. Yeah. So this is durability. This is the story of we call this the rule of 2. The data that has been given to a client exists in at least 2 places. Okay. So now fault tolerance. So what happens when something goes bad? Okay, let's say this node goes down. It doesn't matter that much. It only contained publishers. They're completely redundant. The clients that were connected to them, they just connected somewhere else, and they got the data. Everything's good. What if we lose the sequencer A? At this point, the system grinds to a halt. A human gets paged, and then we have to go fix it. And this is what I mean by a smidge. This is the one thing that we do not have an automatic solution for. And we do not do any sort of automatic leader election or promotion of another sequencer. And that seems weird maybe, but part of the reasoning behind it is that consensus algorithms are really hard to get right. They're really easy to get wrong. And when you get them wrong, maybe even worse things happen when they shouldn't have, when they couldn't have, when nothing bad would have happened. So it's kind of scary to go implement one by ourselves. And if we try to use one off the shelf, well, maybe we start to lose all of the latency and throughput things that we had so carefully tried to build up. But there's another reason why, and it's that hardware's actually pretty reliable. I feel like this is a hot take, but honestly, we have the number of times we've lost a sequencer node is probably less than 10 in the past 8-10 years, where I'm counting the predecessor system to Aria, and it does happen. It does happen. Within the past 6 months or something, we lost the node with the sequencer for our biggest Americas instance, and network card failure. So it just kind of crapped out. Fortunately, it was kind of during the day. It was also before trading, so it was extra fortunate. We were able to kind of get online and assess the situation. It was pretty simple. Press a button, got everything back up and running. Took about it was about 5 minutes of downtime. Not great, but not the worst thing in the world for what we haven't done so far. This is also but also this is going to happen again, right? It's going to keep happening. It's not like we can just keep pushing our luck, and maybe it happens at a worse time, or a time when people aren't at their computers. And so we are actually working on this. But it is a really nuanced problem. And I wanted to talk do a little bit on why. What is this slide? Oh yeah, sorry, this is what I showed. We lost this node. How do we recover from it? A human will go press a button and give us a manual, give us the sequencer, like C, promote it. And now we're back in a good state. Clients just shuffle their connections around. The publishers on C deactivate because of the rule of 2. And the injectors activate. But, OK. So what happens if we do it wrong? What if we promote the wrong sequencer? And this could be like us, humans, or it could be like, you know, the thing trying to heal the system. The rule of 2 is that all the data appears in 2 nodes. And here, that is true. 1 through 5 is in 2 of the nodes. Everything is good. But then we lose node A, which was the sequencer. And in this case, we have to promote something. And we accidentally promote the C instead. So there are some clients that were connected to the B node that have seen up through the first 5 messages. But now C is active. And it doesn't know about 4 and 5. And so, of course, we start appending to C. And so we get 6, we get 7, we get 8. But those, they can't like replicate to this node B anymore because node B has conflicting data. I mean, maybe the 8 makes it. But now you have these 2 completely divergent timelines where some of the clients disagree with the other ones. There's still just one sequencer, which is great. But there's like a subtle like history problem where things forked, and it's not clear how it's going to resolve or what it's going to cause. So this is like a kind of a safety issue. The second one would be promoting two sequencers. So in this case, I just slimmed it down to 2. So we've got node A, node B. Everything is good. Node A goes dark. We've lost node A. We need to promote a backup. Node B is safe. Let's also assume there's a node C that, you know, is also available. So we promote node B. Great. There we go. We can append. Everything's looking good. And just kidding, node A was not offline. It was just partitioned. And now it's back. And turns out that it was partitioned with some clients that had like been sequencing messages. And so not only did we like fork the stream, fork the log into like two series, we now have 2 things that are the source of truth for new appends. And so this is like a really bad outcome. This has not happened before, and neither has the other one. But it's like, these are things that we're worried about. Like, if we build a system that accidentally makes this happen, especially when there was no outage or something, that feels concerning. Right. Do we have regrets? Certainly some. The redundancy story is not one of them, I think. It has worked out well so far. It's a looming threat, definitely. But we made a system that was really easy for people to use. And people have built some like really powerful things on top of it, like because of this total ordering property and because of the way that you can scale it out. We made it, we have some like extra things exposed to let you build even more advanced features, like sort of like your own consistency guarantees or your own like durability guarantees that cross regions or something like that. These are things that you can kind of build by yourself if you are willing to put in the effort. Again, like why not just use another database off the shelf? But like sometimes you are doing something very complicated and that is just one part of a bigger system. And it can be worth it to invest that effort. Cool, so it's over. Not really. I was going to talk about a few things, but then it got long. So in all, total ordering is great. It's very powerful when you can afford it. And if you like architect a system with some intention in your design, you can get pretty far with it. And skip, 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 skip. OK, now it's over.
So I know you covered this at one point, but my brain missed it. What is the main point of Aria? Like, what are you using this for day? Like, why is it so helpful to you? Like, I get the log ordering, I get all that. But like, what's the point? You know?
What do you do? Yeah, why use Arya? I guess like I can like pull out random examples.
Okay.
I feel like there are things that are simple where maybe you are just, I mean, like, honestly, there is, like, trying to find, like, one that makes sense. I guess one example is, like, you have a trading system that wants to share some information with all of the other trading systems. And that's, like, a really expensive thing to do if they had to talk to all of them. And so you can kind of put it in one place and let us do the distribution, and then everyone can kind of keep their own state machine. And so you prevent a lot of communication by just having it in one central place. But a slightly more complicated, or actually an easier, how about this? A more fun example is that our source control like tool, we call Iron, it's kind of like the way that we manage the fact that we are still on Mercurial, and it is just a server with some RPCs, and like you can talk to it programmatically, but like it was just one process for a long time, and they had no like. It was hard to kind of scale out, and it was not using a database. It was kind of built on this log-based stuff where it wasn't keeping, you know, a history, just personal. But you can kind of, once they started taking every request from a user and putting it on the log, and then waiting for it to be sequenced, and then responding to that, what you have is now like you can spin up a bunch of servers, they can all watch that happen, and they can all say like, oh, I know, they just made this change. I'm gonna go make the change in my own state too. And so now you have a bunch of replicas that are able of reading the state of the world very fast. Like you can run one in Asia, and it can give answers very quickly to people that are very far away from the single central server that's in New York or something like that. So there's a lot of like, consensus things that you can build in synchronization, hot, like redundancy, failover stuff. Yeah, is that okay? Cool.
Yes, thank you.
I'll take someone there, yeah.
Right, so I think you said that the connection between the clients and the injectors was multicast, but what about the connection between the producers and the clients? Is that much or all, or what?
Yeah, so the actual only, going back to that, this slide about, yeah. The only multicast that we have, well, sorry, not only, most of the connections between the clients and the green and the blue stuff is TCP. And that is because like clients are kind of pipelining a bunch of stuff, and like there's not a lot of like performance to squeeze out of that. The internal protocol that we use for disseminating data, that is multicast. We also have the ability to publish multicast data to clients, but it's kind of like, multicast is not like an easy thing to opt into, so it's really for people that have, you know, tens of thousands of processes wanting the same stuff, and that's a lot of TCP connections, so we use multicast. Yeah.
For this 30 microsecond round trip time, what is the distribution over the size of messages?
Oh, that's a good question. What is the distribution over the size of messages for a 30 microsecond round trip time? Basically, it is a single line, I think, because all messages they fit inside one UDP packet. And so that is how we like, you know, put them on multicast, or that is one of the things that we do. And so the injector I mentioned does this chunking mechanism where it will split up a large packet into many smaller fragments that we can deliver, which also has the benefit of like not clogging up like you know, if a client wants to send a giant message, we can do it by like kind of sprinkling in fragments of it throughout in that totally ordered stream. But when reassembling it, you only count the final packet as the point where it is done. So that's your total ordering mechanism for that.
And how large are your UDP packets on your?
Oh, how large? Sorry, yeah. We use like the plain vanilla network. It's just the 1472 bytes minus headers, like down to 1448.
Actually, also on that 30 microsecond point, just wondering if you have a perspective on how quickly you see that maybe improving, or for context, what that speed used to be.
Yeah, 30 microseconds, improving, question mark. Actually, it's kind of been that way since the beginning. I think like this is really about the fact that we architected this with latency in mind from day one and had experience of doing it with another system. I could actually, I mean, I think I can, it is going to get better. The one thing to say is like the injector to sequencer protocol used to be over UDP multicast, but we are now, because they are now co-located, it is switching to just shared memory ring buffers. And we do measure the injector to sequencer round trip times as well. And those went from like, I don't know, 10 mics down to like a few, 4 mics or something sometimes. So like net effect on clients, maybe there is something there. But I also think that like, I don't know, there's like still, I think there's still a lot of variability because within our system, we might be able to process that message in 30 mics, but like a client also has to be able to like read it off of their network card in 30 mics for it to actually be 30 mics. And if they're just like, you know, chilling, spending 50 milliseconds on the last message, it's not going to be, they're not going to have a 30 mic experience. So I don't know if like we're super excited about getting the number lower. And in fact, most of our goals are around kind of like increasing the throughput and the way that we can efficiently retrieve old data.
Could the bandwidth of the messages ever exceed the resolution of the sequencer? You said it was literally a wall clock, but like...
Oh, right. So I said that the sequencer is stamping a number onto the packet. It's using its wall clock, strictly increasing, not monotonically increasing. Every number is unique. And I don't know if it could ever exceed it, but we're not going to take our chances, so we definitely cheat. Like the clock is really, you know, either the wall clock or whatever the last number we stamped plus 1 nanosecond, plus 1 nanosecond. And in fact, we actually do this whenever we get, sometimes the injectors will batch up a bunch of messages and we will not check our wall clock time for each one. We're just going to add 1 nanosecond to each one as an approximation, because it's not meant to be a strict stream time. It's a time. It's just a.
So like if you got 10 within 1/2 a nanosecond, it wouldn't matter.
Yep, they would just be 10 consecutive timestamps.
When you have this requirement of like two of the 3 must have the data, do they also all have to have the same shared prefix before they append?
Yeah, so this is kind of like getting into this sort of thing where like 2 of them had to have the data, like the rule of 2. Is that right?
Well,
we're
it's
talking
different
about
than this because like if you said only 2 had to, unless there's an order that you're always replicating, then like node B could have 4, node C could have 5, and only eventually might they catch up or something like that.
So like, could node B have 4? Could node C have 5? Like, what happens then? So, remember how I said this is like a totally ordered stream? That means that our servers also want to treat it as a totally ordered stream. So if for some reason node C got 5, it would say, hold on a sec, I missed 4. It's going to stop and go get 4 before it can even process 5. And part of this is like, well, we can't send 5 downstream, but because we don't know if 4 needs to come before it. But it's also because we actually do a lot of our own coordination on the same stream. When we're trying to like coordinate, new like partitioning schemes, or like trying to partitioning in like a different sense, trying to make sure that there's not an exactly once or a client request that gets double appended. We use the stream as a coordination mechanism for that. Yeah, back there.
And clients detect when they're becoming terminally behind, like the log is extending out in front of them faster than they are processing it, so they're like just getting further and further behind. Is that in the client can like query and figure out that, oh, I'm not processing fast enough and therefore I'm screwed, or what happens?
Yeah, so the question is like, what if you are falling behind, you're not processing fast enough, and the log is increasing faster than your rate of consumption? For like clients, this is the green client boxes. This is not uncommon at all. Sometimes people write really spiky workloads. Sometimes the clients are kind of just not built with like the best performance engineering in mind, or sometimes they hit a single message that is like really expensive. Lots of things happen, but like you can generally, what generally happens is like, well, you get an alert because one of the benefits of having the sequencer stamp its own wall clock is that you can compare its wall clock to your wall clock, and you can say, hold on a second, this message was from 30 seconds ago. I am behind, and then you can like raise an alert to the team and they can go check it out. And this is like a very common thing that happens. It is also a thing that has happened to us at times where our servers cannot keep up with the rate of the stream progressing. And that's kind of that's a pretty bad thing. We don't want that to ever happen, but we have, we try to treat those as like bugs that we have to fix. Yeah.
Small question. So you said you basically have out a 10 gigabit network card, and that's your current problem. 10 gigabits is kind of big for hardware that you own in your own data center. So have you tried on bigger network cards, and what does it cap out at there?
You were talking about 10G? Is that? Yeah. Okay. So like the question, I talked about how like we use 10 gig network links as like our sequencer limit, and that's kind of where it stops. That is kind of intentional to some degree. We actually do have 25G links all over the place, especially for when we're doing these publisher stuff. Like when we're serving clients, we might get one message from a client that gets appended, and we have to send it to 1,000 different consumers. And this fan out ratio of 1 to 1,000 is like pretty massive. Fortunately, we can multicast out to a lot of publishers and have them all send over 25G links, and that's pretty effective. So yes, 25G totally works. We don't do it for the sequencer, and that's kind of on purpose because there's a little bit of concern that one, if the sequencer could sequence that fast, things might really fall behind. And the other is actually microbursting, where even though you might not sequence at like 25 gig, or you might even average out at about like 1 gig, you can microburst at 25 gig for some small fraction of a second, and that causes drops somewhere. And drops are kind of like really painful because, like we were talking about, if you miss 4 and you get 5, you have to go get 4, and that's slow. And so we try to like limit the amount of dropping that we have to deal with. Yeah.
2 questions. Like, I might miss this, but one, like between the sequencer and the publisher, like what like substrate is the data like actually stored on, like for the records? Like is it like a log file on a disk or something like that?
Yeah. So like, what is the data stored on in these little disk icon things? I was definitely a little vague. Like, part of it is a ring buffer of data, and that is about, I want to say like 4 gigabytes. It's just like a large ring buffer. we write to disk as fast as we can while we're doing that, and it is kind of just a single contiguous file that gets segmented up. We are kind of changing it a little bit in the future. Like I said, things change, but we only keep certain amount of the data on these nodes, and then we ship data off to these like more bulk long-term storage nodes, so that if a client was really far behind, if a client just wanted to go replay messages from like last week, you could do that. You can go back a month. You can go back for, assuming we are retaining the data, you can go back and go read what happened, you know, on August of last year. But that's not stored on these servers. And so you can kind of think of this as just like the tail of this log, but enough of a tail that, but between the ring buffer and the thing on the disk and the thing on the other server, the whole picture is there. And the thing on the cold storage, like all of the data is somewhere, it's just not clear where it is exactly at any given point in time.
The second question, like, you mentioned like if there's like a node outage, you know, it's like really bad because there's no like automatic leader election or anything. But if you like have a planned change, you want to like, you know, patch this sequencer with like a code fix or something. Is there a safe way to do it?
Yeah. Like if there's we don't have automatic handling, but what about planned things? Absolutely, yes. This happens all the time. In fact, it happens every week because we specifically want to make sure that we can like exercise the handoff mechanism, and we want to be able to make sure that we can hand off between different data centers, and like make sure everything kind of falls over like nicely. We typically kind of do this over the weekend, and the like. Oh, and there are sometimes just maintenance events for specific hosts that get scheduled. And when we detect like that schedule thing coming up, we will like automatically, with a job, preemptively run this script. But this script is like, it has to pass a lot of checks. It like the active sequencer has to be active. And that's how we get that guarantee that it's not gonna like blow up. All right, thanks everyone.
Thank you everyone for coming. Thank you so much Doug and Olivia for speaking. Thank you Trail of Bits folks for hosting us. And if you want to hang out, I hope you come to Strong Rope Brewery. Just follow the crowd. It's around the corner. They have non-alcoholic drinks. You don't have to drink alcohol. We'll see you next time.
It's not Strong Rope anymore. It's now Forever Home Brew.